So hello students, today we'll be seeing about a topic called as binary trie. Okay, so this topic I have discussed in the last class, but I felt like this topic requires little more explanation. So I'll be repeating the same topic and then we'll be moving to the next version of this binary trie, which is the multi-bit trie. Okay. So before learning about the binary tries, let me teach you what is the IP prefix, okay? And you all know, like when a packet arrives at the router, so there is a router, and so let's imagine that this as a router, and the packet is arriving at the router, okay? And the packet comprises of actually, let's take two parts. The first part is the address part and or the header part, okay? So let's take the first part as the header part and second part as the payload, which is nothing but the actual data. So as soon as a packet arrives at the router, we have learned about two types of interfaces, right? One is ingress interface and another is egress interface, okay? So egress and ingress. So ingress is nothing but the incoming interface and egress is nothing but the outgoing interface, right? Okay, so as soon as a packet arrives at the router has to take some series of actions, right? So as we all have learned in the previous classes, we know like what type of actions the router will take. So first, the router, what it does is like it will identify the header part of the incoming packet, and then from the header part, it will try to segregate the destination IP address, okay? Destination address, okay? And this destination address will consist of two parts. The first part will be the host part, the network part. The first part will be the network part and the second part will be the host part. So the first thing we need to identify here is the network part. So once the network part is identified, then it is easy to find the host associated under that particular network, right? So like say for example, this is a street and here is a house and the house number is 24 and the street number is say Gandhi Nagar, and so we need to find Gandhi Nagar first, right? So likewise, we need to find the network part first and then we need to find the exact host, which is nothing but the house name here. So which is nothing but the host ID here, okay? So we look into the router, look into the destination address for these two parts and it will segregate this network part, okay? And this network part is also called as IP prefix. This network part is also called as IP prefix. So it is being segregated, right? And next what happens is like once the IP prefix is segregated, then it would actually first by looking into the destination IP address itself, it can also choose which forwarding table actually this incoming destination address actually matches, okay? Like we have different classes of address, right? So we have class A, class B, C, D and E. So D and E will leave it and we'll consider only A, B and C. So by looking into the destination address, one can easily identify to which class this particular IP address belongs to, and then be careful in selecting that forwarding table alone. Suppose if it is class C, then select the forwarding table that matches only with the class C, okay? So that table is fetched and once that table is found, then the IP prefix is extracted from the destination address. So two things is happening here. So to make you clear once again, so the destination address the router have at its hand, okay? from this destination address, it is easy to identify which class this address belongs to. Okay. So if the class is, for example, it is A, then choose the class A forwarding table. Class A forwarding table. Okay. Class A forwarding table is chosen. And then try to identify the IP prefix from this destination address. Okay, from this destination address, try to identify the IP prefix. And then with this IP prefix, from on the chosen forwarding table, do the searching. Okay, the search would be, obviously, it's a linear search. Linear search is nothing but searching one by one. So it is like searching one by one. So actually it is a tedious job, right? So because we always say that it is not a single entry or 10 entries or some 20 entries, 100 entries inside the forwarding table. The number of entries inside the forwarding table will be huge. So let's take the forwarding table for example. So imagine this is a forwarding table of class A, class A forwarding table. It comprises of two columns. Each entry consists of two parts. The first part is the actual prefix, and the second part is the interface that it has to take. Right? Our prime goal here is like receive the package in the router, inspect the destination address, find the corresponding table, and then segregate the or retrieve the IP prefix from the destination address, and then have a search on the forwarding table based on the prefix. Okay. So suppose if the IP prefix from this destination address is 101. Okay. So there will be like many prefixes that begins with 0, 1, 0, 1, 1 will be there, like 1, 0, 0, 1 will be there. And there is another set of prefix, say for example, 1, 0, 0, 1, 1, 0, and then 1, 0, 1. And each will have its corresponding interface 1, 2, 3, and 4. Okay. So in this case, we have to do uh, a search on sorry. Okay. So if the incoming IP prefix, okay, the destination IP prefix is 101, the search entry begins here. Okay, the search begins here. So first we'll search for 1011. So does it match with 101? No. So we leave and come to the next entry. So we'll continue the search until the desired match is found. So once 101 is encountered, then the interface I4 is taken to exit the packet. Okay, so I4 is the interface that will be taken by the packet from the router to exit. Okay, so that is identified as the best path to send the packet from the router. And this series of works is happening at every router. So whenever an IP packet arrives, the destination address is being taken, and appropriate class table would be identified, and then the IP prefix is taken out from the destination address, and with that IP prefix, search is done on each entry of the table until a match is found. So once the match is found, then the corresponding outgoing interface is taken, and through that interface the packet will be routed. Okay, so that's happening. And now having a table of size 100 entries or like 200 entries, that would be easy for searching if we do linear search. But imagine we are talking about a network where millions of devices are connected, and there will be more number of packets flowing inside the router at a time, and having this kind of table structure and doing linear search one after another would be a tedious job, and the time to search is again huge here. So in order to reduce those things, okay, so we introduce a concept called as binary tries. So binary trie is nothing but a tree-like structure. Binary trie is a tree-like structure, and it comprises of root node and child nodes. Okay, child nodes, and every node can have uh, 0, 1, or 2 descendants. Descendants are nothing but the child nodes. Okay, so either there could be no child, there could be single child, or there could be two child, not more than two. Okay, so that's how. And the main motive behind this construction of binary tries is like the search time has to be reduced. So that is the ultimate motive. And so let's see how this binary trie would help in organizing this routing table into a tree-like structure, and how searching could be performed. Okay, and as you all know, there will be a root node, and this root node can have two branches. The first branch, which is the left branch, that always will be marked with bit 0, and the right branch will always be marked with bit 1. Okay, and so from there the tree tries to expand. Okay, uh, let's say for example, so I'll show you with an example what's given in your textbook. Wait for a minute, I'll share another screen. Okay. Yeah. So let's see. So these are the prefixes given. P1, P2, P3, P4, P5, P6 up to P9 prefixes are given. So P1 prefix is given as 0 star, which means 0 followed by any number of bits. And P2 star is like 0001 star. And likewise, the prefixes are given. So you can see the length of the prefixes are of different types, different length. Okay, so this is how this binary trie is being constructed according to this given prefixes. Okay, so we'll start with the root node. So we have the root node here, and this root node comprises of left branch and the right branch, and the left branch is labeled with 0 and right branch is labeled with 1. And then we have because the prefix P1 says it is 0 and more, right? So but actually it carries P1 signifies only 0, but the dissonance of P1 can have other bits also, right? So we have the settings done here. 1 second, right? So you can see, so 0 is labeled, and it can always yield to or lead to P1, okay? And P1 is a prefix, so that's why it is being shaded. Okay, I have shaded P1 as since it is a prefix. So prefix nodes are shaded, non-prefix nodes are not shaded. And next P2, P2 also begins with 0, so we'll take the left branch, and then the second bit is also 0, so it again takes the left branch, and the third bit is again 0, again takes the left branch, and the fourth bit is 0, takes the left branch, and next the last bit is 1. Okay, so it takes the right branch, and it is marked as P2. Okay, so P2 is again a prefix, but it has to be shaded, right? Sorry, I haven't shaded, so it must be shaded. So P1 is marked and P2 is marked. And now come to P3. P3 is again, it's beginning with 0. So we have to take the left branch. Okay. And then the second bit is 0. So again, it has to take this branch and the left branch. And the third bit is 1. So we move to the 1 second. Okay, so okay, so now let's move to the P4 prefix. P4 is like it begins with bit 1. So it takes the right branch. So it's 1. And so P4 is marked as a prefix here. Okay. And it doesn't expand further according to this prefix. But there will be more dissonance coming up. So as of now, it is 1. And that's why star has been marked here. And now P5, it begins with 1, so we take the right branch. And second bit is 0, so we take the left branch. Okay. And third bit is 0 again, takes the left branch. And then again we have 0, so take the left branch and mark it as P5. Okay, so P5 is a prefix and it has been shaded. And next is P6. So P6 is like it begins with 1. So take the right branch and come to P4. So the bit doesn't stop there. So it has another bit called a 0. So it takes the left branch. And then next bit is 0. So it takes again the left branch. Next bit is 1. So it takes the right branch. Okay. So 1, 0, 0, 1. Okay, sorry, this one. 1, 0, 0, 1. So this is marked as a prefix and it is marked as P6. And now let's take P7. It also begins with 1. So we have to take this particular way. And next is 0. So come to this way. Next is 1. So go right. Next is 0. Go left and mark it as P7. Okay. Now P8 again. Its first bit is 1. So the right branch is taken and P4 has been reached. But P4 cannot be considered as the best matching prefix because it has many more bits following. So 0 will be taken and so it takes the left branch and then it third bit is 1. So it takes the right branch and fourth bit is also again 1. So it takes the right branch again and it has been marked as P8. Okay. And now triple 1, P9. So take right branch is taken, again the right branch is taken, again the right branch is taken to form 1, 1, 1 and the node is being marked as P9. Okay. So all the prefixes are shaded with gray color. Okay, they are gray shaded. And other nodes remains like it is not colored with any of the colors. Okay. So you can easily identify from this binary trie that each node has at most like either 0, 1 or 2 descendants, right? 2 childs. And there is a root node also at the top. Okay. So the root node on the root, at the root node only. So this is how the binary trie organization of the prefixes is being given. Okay. And you know, like there are nodes P1, P4, P2, P3, P5, P6, P7, P8, P9 are prefixes, but they are stored in a node. And these nodes will have 2 parts. Okay. The nodes comprises of, each node comprises of 2 parts. The first part is the next hop to be taken. And the second part is the pointer to the next subtrie. Okay, pointer to the lower subtrie. Okay. So if next hop information is not available, then it will be marked as null. If pointer is also not available, then it is also marked as null. Okay. So by looking into a node, so as soon as P2 is reached, from there, when the node is inspected, we can find the next hop to which the packet has to be forwarded. And also there will be a pointer too. Okay. If there is no subtrie following this P2, then the pointer will be marked as null. Okay. So now let's move to aggregation prefix and exception prefix. Okay. So here you can always say this P1 as aggregation because P1 is an aggregation of P2 and P3. Why? Because P1 begins with 0 star, right? So the beginning prefix, the beginning bit of the prefix is 0, and it can be followed by any number of zeros and ones. So that's why star has been indicated there. Okay. So we can say like P1 holds the addresses of P2 and P3. So that's why P1 is called as, because you can see P2 as P2 addresses 0, 0. So it's given as P2 is 0, 0, 0, 0, 1. So when P1 is indicating 0 star, which means 0 followed by any number of any zeros and ones, right? So P2 is again 0 followed by 0, 0, 0, 1 star. So which means it is falling as a part of P1. And P3 again, if you take, it is beginning with 0, then followed by 0, 1. So again, it is a part of P1. So P2 is a part of P1 and P3 is also part of P1. And this P2 could be written as 0 star. And P3 could also be written as P0 star in general. Okay, so when they become so specific, we write P2 as 0, 0, 0, 0, 1. But when they become so general, they could also be called as 0 star, because 0 followed by any number of zeros and ones, right? So P1, so now we can call P1 as the aggregation prefix, because it is a combination of P2 and P3. It holds the addresses of P2 and P3. Okay, so it holds the prefix, exception prefix P2 and P3. So that's why P1 is called as aggregation prefix. But P2 and P3, since they are part of P1, they are called as exception prefix. And these exception prefix are always descendants of the aggregation prefix. Okay, so they are always called as descendants of the aggregation prefix. Okay, so now let's do a search operation. Okay, so there are many. The search operation could be performed on a binary trie. Update operation could be performed. Insertion operation also could be performed. Deletion also is possible. So all operations what you do with a table is made possible with the binary trie also. Okay, now let's see. We have an IP address with the destination IP prefix as 001. Okay, now we have to inspect bit by bit into the binary tree and find the appropriate prefix node, and from that node I try to identify the next hop it has to be taken. It has to take. Okay, and so let's see, begin the search. It is 001. Okay, so we are going to search on this binary trie. So the first bit is 0, right? So we are going to search bit by bit. So the first bit is 0, right? So I'll choose another color. Okay, so what is the first bit? First bit is 0. So we have to inspect the root node and we have to find the two branches. Since the first bit is 0, we cannot take the right branch because it is marked as 1. We can always take the left branch because it is marked as 0. So on inspecting the first bit from the incoming destination IP prefix, we have reached P1, right? P1 has been reached. But we cannot mark P1 as the best matching prefix. P1 is also a prefix, but it is not the best matching prefix because it has another 2 bits following, right? Another 0 is there, another 1 is there. Only the first bit is being inspected as of now. Okay, so now the search continues with the second bit. Second bit is again 0. So now take the root that has been marked as 0 from prefix P1. So this is the root, right? This path has been taken and this particular node is reached. And this is not a prefix node, so we cannot mark this as the best matching prefix. And then we cannot stop the search here. We have to proceed with the search as the next bit it says is 1. So now the searching has ended, stopped, means like it has reached this level, and from here the next bit is actually 1 in the incoming IP prefix. So we have to take this particular route and we have come to the prefix P3. So P3 is the best, it is already a prefix, right? 001 is already a prefix. So P3 is marked as the best matching prefix here. 001, right? So this 0, and this 1. So this is considered as the best matching prefix, and P3 will be remembered for the best matching prefix for the incoming IP address with destination IP prefixes 001. Okay, and then P3 will be inspected, and it will have like two parts. The first part representing the next hop to be taken, and second part will be representing to the next subtrie. Since it doesn't have a subtrie, it could be marked as null in this example. But this is not the size of the binary trie. We could always imagine that would be present inside a router. So it would be huge in structure, right? So this is for your better understanding. Small kind of tree is being given. Okay, so this is how search operation is being done. So we have to inspect bit by bit and take the appropriate path according to the tree given, and then find the best matching prefix. So P3 is the best matching prefix here. Okay, so we can say P3 as the best matching prefix. And next is insertion. Okay, so if you want to insert a new node, which is a new prefix, which is 110. Okay, so where can you insert 110 in this trie? 110, we are going to insert 110. Where can we insert? So the first bit is 1, so take the right branch from the root node. Then the second bit is 1, so we have to take the right branch. The third bit is 0. Okay, so we have only the right branch taken from here. We don't have the left branch with 0. So you can just mark 0 here, and then you can enter P10. Okay, so this is the node here. Okay, and say for example, if you have to insert a 0110. Okay, 0110, if you need to insert, the search has to, the insertion prefix is 0110. Okay, so if you have to insert, let me pick another color for you. So if you have to insert, let's take another. Yeah. So if you have to insert this 0110, the left path has to be taken. So prefix P1 is reached, and the next bit is 1. So go to the right. Since it is 1. Okay. So this is the left first bit 0, and the second bit is 1. But there is no one branch here. So we have to form the branch and mark it as 1, and then you have to enter another node, and you cannot label the node because it is not a prefix. And then you have another 1. So the third bit is 1 again. So another 1, you have another node, and then finally 0. You can have a left branch for this, and then mark the prefix as P, I think it's P11. Okay, so this is how the search continues. So once you reach the end of the prefix, you can mark that particular node as the best prefix. Okay, you can shade it and consider that it is one of the prefix that could be fetched in the future for taking up exit interface from the router. Okay, so this is how the inserting operation occurs. So when you see, as I said, each entry will have two fields. The first is the next hop, and second is the pointer to the subtrie. If they are not present, then they could be marked as null. And now you could also find the search complexity, like any algorithm. So binary trie is an algorithm, right? And any algorithm, when it is being run, it always have its own performance measures. Okay, so we'll evaluate its performance. So we are performing many operations like search, update, delete, and also insert, right? And every operation will have its own complexity. And if you take W as the length of the address, okay, so usually IPv4 IP address size is 32 bits, okay, 32 bits. So if W is 32 bits, then if you want to have a search, sometimes at the worst case, you have to perform 32 searches. So that's why it's given as order of W, the search complexity. And if you have to update also, you need to take sometimes 32 kind of searches. So that's why it's given again 0, order of W, big O of W. And similarly, the complexity for deletion and insertion too, they all form the same order. Why? Because sometimes the search may be ending at the first level of the tree itself. Sometimes the search continues, okay? And because there is a possibility of having single child nodes also, and the length of the traversal will be very high. So the time taken to search the entire bit of the incoming IP address is sometimes required. And it may take you so deeper within the tree, and sometimes you may end up in searching 32 times, okay? Because you are inspecting bit after bit from the incoming IP prefixes. And also the kind of memory access you do. Like for every bit, the memory access has to be done, right? So these are all some of the complexities associated with this binary trie, okay? So this binary trie has two drawbacks, okay? So the first drawback with this binary trie is, so drawback. The first drawback is the search time, okay? And the second drawback is the memory access. Okay, so these are all actually is increasing. The search time is higher and the memory access is also high. So in order to overcome this drawback, another, a modification on the binary trie has happened, and that kind of algorithm is called as the path compression on binary trie. Path compression on binary trie. Okay. So path compression technique could be implemented on the binary trie to shrink the tree and reduce the level of trees and reduce the depth of the tree and try to reduce the search time as well as try to reduce the memory access. So how it is made possible? So binary trie will always support arbitrary length of prefixes, but sometimes there is a possibility that like one child nodes also exist. So in order to like when there is one child node existing, like there are more levels in which there is only single child present. And this will increase the search time and the memory access also. Okay. So our objective is to reduce the search time and the memory access. So how it could be possible with this path compression technique is like, do not involve one child node bits. Okay. We are trying to eliminate them. So we are going to eliminate the one child node in the binary trie, and we are going to compress the tree so that the search time and the memory access will be reduced. Okay, so how it is done? So let's see with an example. So I'll show you only the left part of the tree, how it is getting compressed. Okay, so now come to the trie, binary trie. So here I'll try to expand this. Okay. So you can always see starting from the root node, okay, let's consider only the left bits alone, the left branch alone, and don't try to include the a new prefix that has been inserted. Let's leave this. Okay, so I'll try to erase. So I'll try to erase this. Okay, so we are not going to involve this new prefix that has been inserted. Okay, so let's consider only up to this. Now let's begin from the root. So this is a left branch. This root has two branches, the left branch and the right branch. Okay, so it's fine, the tree is complete. And now come from, there is a edge that emerges from T1 and then to another node. Okay, but this node also comprises of two child. Okay, the left child and the right child. No issues here too. But you can see here there is only one child node. And you can see here there are only one child nodes. Right? Yes. Sorry. So this comprises of two child nodes, right? We cannot say that. No, 1 second. Okay. So you can see here. These are all only single child nodes. Okay. So now we are trying to eliminate these single child nodes and then we are going to compress the tree. Okay. So how that could be made possible? And we should not always forget the number of bits because these single child nodes also have bits associated, right? We should not forget that. But somewhere it must be stored. And how it is made possible? Let's see. So, as we all know from the root node, there is a left branch and that is marked with 0. And now it is reaching P1. And what we are trying to do is, we are trying to eliminate all this. Okay, let's see. Now I think you can see everything in a single window. Right? Yes. Yeah. So what's happening here is we are trying to eliminate the single child nodes. So this node is removed because this I cannot remove because this is a prefix. Okay, prefix nodes I cannot remove. Only the other nodes could be removed. So this node is removed, this node is discarded, and again this node is discarded. Okay, and this P3, which is acting as a left branch of P1, is now attached to P3, P1 directly. This P3, which is a left branch of P1, is now attached as the right branch of P3. And this P2 is now attached as the left branch of P1. Okay, so that's all. P3 is attached as the right branch of P1 and P2 is attached as the left branch of P1. Okay, so these are all now prefix nodes. And now you can always mark the prefix label also. Okay, so this carries 001 star, this carries 00001 star, and this prefix carries 0 star. Okay, so now you can imagine a label called as trie that has been put within a box, which means the number of nodes that has been removed. Okay, so the number of nodes that has been removed are 1, 2, and 3. These 3 nodes are removed, right? So that label is put inside this box, which means we have to skip 3 bits while inspecting. So we are not going to inspect bit by bit. Okay, so let's take the search that comes in as 00100010. Okay, so the first bit, so the root node will always have the label as 1. Okay, which says that just inspect the first bit. So the first bit is being inspected, which is 0. So now take the left branch, and when it reaches P1, it says like skip 3 bits, because what is attached with the box as 3. So skip 3 bits, means go to the third bit. So what is the third bit? Here it is 1. So 1 is the path, this is 0 and this is 1. 1 is the right branch. So it comes to P3. What is in P3? 001. So it has reached 001. And then it has remaining bits also, but there are no more search that could be done because there is no subtrie following P3. So the search stops there, and P3 is marked as the best matching prefix, and P3 will be looked up for the next hop, and the router will route the packet according to the next hop information available at P3. So hope you understand. It is little confusing for you, I think. So I'll repeat the same again. So let's consider a fresh tree I'll draw for you. So there is a root node, and this root node is having a left branch that is labeled 0, and that is leading to a prefix P1, which is 0 star. Okay, so it is a prefix P1, which is 0 star. And then from this prefix, there is another from this prefix, there is another node, and this node comprises of 2 branches, the left branch and the right branch. So this is again, since it is a left branch, it will be marked as 0. And since it is a left branch marked as 0, since the right branch marked as 1, so this is leading to P3, which is the prefix, and this again is leading to another node, and then it is leading to another node, and from there it leads to the right child, which is P2, that is again a prefix. So this is 0. So you can see the tree. So it also has its right subtree also. Okay. So now let's look into the left tree alone. So this is the root node. Okay. So we are going to eliminate, path compression is nothing but eliminate the single child node so that the search time and the memory access get reduced. Okay. So and those nodes that you are going to eliminate must be non-prefix nodes. Okay. So this is one non-prefix node. This is another non-prefix node. This is another non-prefix node. So only these nodes we can eliminate. Okay. So we are eliminating how many nodes? Actually, this is not a single child node, but there is no way, because we cannot eliminate this. Actually, this is also a single child node. So this could also cannot be eliminated. P1, P3, and P2 cannot be eliminated, but the remaining nodes can be eliminated. Okay. So we eliminate all these 3 nodes and then mark the label as, like we formed the compressed tree as. So this is the root node that always says inspect the first bit, and then we take the left branch. So there is a prefix P1, and there is a prefix that has the value 0 star, and from there the left child and the right child are formed, and in the left child there are actually it is a single child node in the original trie, right? P1 is a single child node, but the single child node under P1 comprises of 2 childs, and then they later lead to many single child, and that has to be removed, and the tree has to be compressed in such a way that we cannot remove the prefixes. So we can have the P3, which is the right prefix of the non-prefix node, that get attached as the right, though it is left for P1. It is since it is right for the non-prefix node, it is getting attached to the P1 node as the right prefix. Okay, so it is P3. So mark this label 1, and the data with this prefix is 001 star. And then here P2, there is no way to remove P2, but P2 has to be maintained, but the other nodes could be removed. And so it is left branch, so it could be marked as 0, and the prefix is P2, and the bit is 0, 0, 0, 0, 1 star. Okay, so all these bits are combined. 0, 0, 0, 0. So here, this is the first 0, then followed by how many zeros? 3 zeros. 0, 0, 0, and 1. Okay, so that's been combined. Okay, and it says like there are 3 nodes that has been removed, and each node will have its own bit information that has to be inspected if needed. So now there is a packet that's coming with a value. What is that value? Search value. So there is a packet that's arriving with the prefix 001, 01, 0. This has to be checked in the compressed trie. So when the root node is inspected, says us inspect the first bit. So first bit has been inspected, and it comes, it says the first bit is 0. So take the left root, and when it reaches P1, it find that it is 0 star, and since it has trie, subtries, it cannot be marked as the best matching prefix. So it takes the it checks the bit inspection part here. So it says inspect the third bit. So from the given address IP prefix, the third bit has been inspected, so which is 1. Okay, third bit inspected is 1. So the right path is taken. Okay, so when you inspect the prefix value of the right path labeled as 1, it says that it is 001. So it exactly matches with the prefix of like a part of the destination IP address. Okay, IP prefix. So, and then the later things could be marked as a star because we don't have any further subtries following P3. And this star can represent 0, 1, 0. So the entire match has been found, and not the entire, the partial match is only found. And with that partial prefix, because since we don't have furthermore subtries to inspect, we can find the next hop information from this particular node and then try to reroute the packet. Okay, so that's how this compressed binary trie is being taken up. And if you want to perform this kind of search, okay, when you come up with the binary trie, the search complexity would be very much less, because to find 001, there you have to take some 3 steps, right? But here you are taking only 2 steps. So the search number of searches is getting reduced. And one more thing is like if you and the number of memory accesses, only 2 times the memory has been accessed to find 001. But there, if you want to find 001 in binary trie, 3 times, because since each bit has been inspected, each time the bit is inspected, then memory has to be accessed. So 3 times for finding 001 with this example because 001 prefix is available. Okay, so it takes three times the memory access. Okay, three times the memory has to be accessed, whereas in this case it is only 2 times. So which means 1 time is getting reduced here. So ultimately, if you could see, there must be a greater reduction in the memory access as well as in the memory access as well as the search time. Okay, the number of searches you do, that is getting reduced in a path compressed binary trie. Okay, and this concept has been taken from an algorithm called as Patricia algorithm. Okay, the algorithm is called as Patricia algorithm, and this algorithm is being actually formed for strings. Okay, only for string data it has been formulated, and the same concept is being now applied to this IP prefixes also to compress the number of searches, the binary trie, so that the number of searches as well as the number of memory access is getting reduced. So that's all for today. So I have given you a detailed explanation about what is binary trie, why binary trie is being required, and so actually it is for easy lookup. Okay, and this binary trie, what are the drawbacks within that, and how these drawbacks could be overcome with the help of this path compressed binary trie. Thank you. So the next topic, multi-bit trie, will be posted very soon. Thank you.